You're about to watch an extract on giant covalent bonding from one of my live TikTok lessons. So if you find it useful, make sure hit that like button and consider subscribing so you can get updates on when more of these videos become available. And who knows, it might help you pass your exam. When we were looking at simple covalent, they only had a couple of atoms. Lots of different separate molecules, but only a couple in every molecule. When we move to giant, we're going to have hundreds of these. There's going to be hundreds and hundreds of atoms stuck together. So I'll give you a perfect example in a second. If you had carbon at like the center, it has 4 bonds, or 4 electrons to have 4 bonds. If it decides it wants to bond with like another carbon, that carbon would also be able to have 4 bonds. This is where it starts to get a bit bigger and more ridiculous. So you'll notice here that I'm putting in lots of carbons because carbon is a really good example of how giant covalent structures tend to work. They are so happy to keep bonding with more and more carbons every time. So this one, let's say here, will bond with another one here. And it'll keep working its way out and out and out. So you end up getting this ridiculously big structure until eventually you run out of atoms. So actually this is something that happens when we start looking at like making something like diamond. Diamond is made up of all carbons and it ends up getting this kind of pyramid shape. Oh, my circles got so crazy there. But if you look at the shape that's after forming, that's where your diamond shapes come from. It's the idea that you've got more and more carbons branching out and out and out, creating a pyramid on top of a pyramid kind of shape, your diamond structure, okay? With giant covalent, you're just looking at hundreds of these. We're not talking this small amount I've drawn. We're looking at hundreds and hundreds and hundreds and hundreds of them. You get a huge structure, okay? Now, each one of those in there, like I was saying earlier, those are your intramolecular bonds. Those are your covalent bonds, okay? They're inside in the molecule. If you were to have any so in between molecules, you're looking at the very outside. But because there's so many of them, there's so many of those intramolecular bonds, there's so many covalent bonds inside in that structure that the whole thing has a really, really high melting and boiling point. It takes a lot of energy to separate out your diamond and to break them into separate pieces. Really, really hard. Makes this really, really strong. So giant covalent structures tend to be really, really strong, really, really high melting and boiling point. Couple of really good examples. Diamond, like I was saying a while ago. You've got sand. Sand is made up of silicone and oxygen doing this kind of structure. You've got loads of them. You've got graphite, which we'll come on to separately in a minute. But covalent, those giant covalent structures are super strong. Right, the reason why diamonds can't conduct electricity is because all of their electrons are bonded in here somewhere. Now that changes with graphite because graphite will actually have a couple of free electrons, but we'll talk about that more in a second. But internally, if we look at this carbon had 4 electrons, it's bonded all 4, it's not going to conduct any electricity. This one's the same, all 4 are bonded, ain't conduct electricity, not conducting, not conducting. So if we're looking at conduction, you have to have free electrons. The electrons are what carrying your charges for you. That's the key to your conduction. You're taking something that can move and take a charge with it. And they're your electrons because they're the only thing that can carry charges over that distance. So the properties of your giant covalent structure is that it has got high melting and boiling points. Okay? They're very strong. And they don't conduct. Graphite is your exception. So if graphite's the exception, I might as well show you what's happening with graphite. Graphite is slightly different because graphite will have 3 bonds. So you have to imagine that this is one carbon atom. So it's going to have 1 bond going over here, it'll have 1 going down here. This one again, it's got 3 bonds. 1 up here, 1 out there, 1 there. This one has got 1, 2, probably 3 down here. This one will go up here. So that's 1, 2, 3. This one is going to be 1, 2, 3. See how we're starting to get a bit of a shape where you go 1, 2, 3. This is where you get your graphite sheets from. So it's because they're going to end up forming layers on top of each other. So they're going to end up getting this structure. But eventually, the ones at the end, these ones, they're not going to have their full shells filled. So they're going to have free electrons, and those free electrons will conduct. Okay, so graphite will let you conduct. With fullerenes, it's the same idea. You've got these graphite layers, but all we're going to do is we're going to turn them into a shape. So if you can imagine, this is what's happening with your football, okay? That right there, the exact same shape. You've got, imagine that little dot there is your carbon atom, and it's got one bond going down there, one bond going up, and one bond there as well, okay? Each of those little dots in the corners, that is your carbon atom bonding in 3 different directions. So that's where you get this little structure, okay? Your pentagonal rings, okay? Or sorry, not pentagonal, hexagonal rings, because it's going to have 6 sides. 1, 2, 3, 4, 5, 6. Okay, so 6 sides. It's going to have your hexagonal rings. But if you bend all of your that sheet of hexagonal rings, so it was at this point in editing that I realized I'd actually made a mistake with what I'd said there. And when it comes to a buckyball, which is what one of these is, it's actually not all entirely hexagonal rings. You've also got pentagonal rings in there as well, as you can see. So a buckyball is made up of 20 hexagonal rings, which were these ones, and 12 pentagonal rings, which were these ones. Now, if you can imagine that this is all made out of carbons, the gap in the middle has got nothing in there, but this structure itself is actually really, really strong. And this is where we have something called a fullerene. So fullerene is just one of these sheets bent around to create a little capsule. And that's become really useful in the last couple of years because scientists have found a way of being able to put like medical drugs inside the middle of these balls and sending them somewhere into your body. And I would definitely recommend, if you want to look up something really cool and random, look up nanoparticles or nanotubes, because they are these. This is where we're looking at those carbons forming little tubes to be used. It's actually really weird. The way they discovered about these sheets was someone had a graphite pencil and then literally, this is how it went. They got a sheet of sellotape and they put it on top of the pencil on the graphite and they just peeled it off one by one. So if you want to have a go at actually getting little graphite sheets yourself, I recommend get a pencil, create like a little box inside in your like workbook and just get a piece of sellotape, put it on, stick it on with your thumb, press down on it and then peel it off slowly. You'll see exactly what I mean by this tiny layer of graphite.